Good evening, student. Today we are going to see the Coulomb blockade effect. What is the Coulomb blockade effect? Using that blockade effect, how one can construct the single electron transistor. These are the two things we are going to see today. The first thing we are going to see the Coulomb blockade effect. You can ask one question. What is the Coulomb blockade? In general, if you are taking the mesoscopic devices, that means suppose if the device is of length a few micrometer to or some few nanometer, if you are taking the 100 nanometer or 10 nanometer, those devices are called the mesoscopic devices. Example, you can say the quantum dot structure or quantum L structure or quantum wave structure. All the structures are called mesoscopic structure. If you are biasing this structure, suppose if you the quantum mesoscopic structure, if you are giving that, if you are connecting with the two metallic wire, suppose if you are giving putting the charge, what would happen? If because of the dimension is small, the current flow will happen beyond some the threshold voltage. Suppose if you are connecting variable voltages here, beyond some certain voltage, the current flow is happen. The electron can tunnel through this device. This effect is called the Coulomb blockade effect. That means below some threshold voltage there is no conductance, but above some threshold voltage there is a conduction, but this conduction will happen in discrete manner. That means electron can flow in discrete manner. If you are biasing some voltage, one electron can flow. If you are increasing some discrete voltage, then two electron will flow. So you can uh, tunnel the charge carrier in discrete manner. This is a Coulomb blockade effect. Here the definition is given. The mesoscopic device conduction at low bias voltage is not constant. Below threshold voltage, no current flow happen. The device no longer obey the Ohm's law. One can control the single electron using this property. This is called the Coulomb blockade effect. So now we are going to see that the single electron transistor based on the Coulomb blockade effect, how that the single electron transistor is working. That's the thing we are going to see now. So what do you mean by the single electron transistor? Suppose the device which is working based on the Coulomb blockade effect, that device we can call the single electron transistor. So that means it will conduct the single electron, or the transistor, it will amplify the signal by the discrete manner by the electron additive nature. That is called the single electron transistor. Before that, we want to understand what is a tunneling, because classically the object, the electron cannot tunnel, but quantum mechanically, if you are thinking the electron having the dual nature, the particle nature as well as the wave nature, according to the de Broglie, because of the wave nature, the particle can tunnel through the given barrier uh, up to some finite probability. So that's why the first point says that tunneling is possible because of the wave-like properties of the particle. Quantum mechanically, the particle can tunnel through the barrier, but classically it can't tunnel. So this quantum mechanical phenomena, we are here, it's a most important property in the single electron transistor. Here in single electron transistor, we are not going to derive any expression, just we are going to discuss the conceptual part only. Now look at the diagram. It's looking like the MOSFET, metal oxide field effect transistor. There is a one source, then drain. Source is emitting the electron, drain will collect the electron. Then there is a gate. Here we are giving the gate voltage. Then in between the drain and source, there is a quantum structure. Here QD means the quantum dot. The quantum dot structure, that means it is a mesoscopic structure. Then there is a capacitor between the gate as well as the quantum dot structure. This capacitor will tune the energy level of the quantum dot. what will happen means the drain as well as the source is acting as a like source acting as a electron donator. Drain will collect the those electron. The quantum dot act as a resistor up to some below some certain bias voltage. What would happen to the energy level structure of the quantum dots? See the right hand side diagram. It's a y-axis represents the energy axis, then x-axis represents the length of the material. This is the energy axis. Here, the left-hand side shows the source, then right-hand side diagram shows the drain diagram. Here, there are shadow region. This is a electron filled region. Here, one electron has shown. Here also the electron collector region, here lot of electrons will be there, but the center material, the in between drain as well as the source, there is a quantum dot. This energy level will be discrete. Already we have discussed about the energy level because the quantum's dot structure is a few nanometer in size, so the energy level will be discrete. There is no continuous energy level. So electron can occupy only the given energy level. So in between here, this is a quantum dot. In between the source, the quantum dot, there is a one barrier. Then the drain as well as the quantum dot, there is another barrier. You can see these are called the junction region. Then it's barrier region. You can call it junction region. The electron, see here, without biasing, that means it's a normal condition. The allowed energy is not matching with the electronic energy. That means the conduction is zero here. Suppose if you want to ask one question, what is the conductivity sigma? It's a zero now because no electron can tunnel through this device. Suppose if you are giving the after giving the bias, now the we are giving the bias between the drain as well as the source region. If you are giving some bias, that means if you are giving some voltage, what would happen? Still the energy level won't change, but what would we want to do here? Just to give the voltage, the Vg to the gate. What would happen? The capacitance will change between the gate as well as the quantum dot. So this capacitance will tune the energy level. So once if you are giving the Vg is non-zero, the gate voltage is non-zero, it will tune the energy level. That means it will bring down the energy level to the Fermi energy of the left hand side source. So now the electron can tunnel through this barrier. It will occupy the because the energy level in the quantum dot as well as the Fermi energy of the left hand side source, it is matching. So the electron can tunnel through the because the size of the quantum dot will be up to few nanometers, then the junction region will be less than the few nanometers. So electron can easily tunnel because it can see the same energy level in the quantum dot. Then this electron can tunnel through this barrier. Here it is collected in the train. This is a single electron transistor phenomena. So it would be nice to see here with the energy level diagram as well as the block diagram for the quantum well structure. Here in this slide, the diagram shown here, it is an the current versus the biasing voltage, the charge versus the biasing voltage. Look at here, the if the biasing voltage is like 1 volt, there is only one electron is allowed through the quantum dot. It's up to the next biasing voltage, it will be constant. Then after some threshold voltage, there is one more electron is allowed. Then after some voltage, there is three more electron is allowed. So the electron is allowing through the quantum dot in discrete manner. Here the left hand side diagram shows the current versus the biasing voltage. It's looking like the staircase structure. That means it represents the electron flowing or the electron passing through the quantum dot in discrete manner. It is not continuous manner. Suppose if the biasing voltage around the 6, then the current will be around approximately it's a 3. That represents only the 3 per second. Only the 3 electron can flow through the given quantum dot. What would happen at this low biasing voltage? There is a Coulomb repulsion between the electron play an important role. the Coulomb repulsion strong enough to it never allowed two electron through the transistor. That means if the one electron is flowing through the transistor, then another electron is blocked by the Coulomb repulsion. So it will repel the another electron. It can't flow the quantum dot because only single electronic energy level is seen by the electron. So the repulsive force between the electron will be large. So electron will be allowing through the quantum dot a single manner. So that is the important concept we want to know from this slide. There are three conditions we got to achieve. Three conditions we need to satisfy to achieve the single electron transistor. SCT means S means single, E means electron, T means transistor, single electron transistor. The first condition, it should satisfy the bias voltage should be less than the electron charge divided by the capacitance of the quantum dot, because the quantum dot is in between two source as well as the drain. So there is a capacitor, it will act like an insulator. Once if the biasing voltage exceeding this voltage, that means E by C, then the electron can flow through the quantum dot. So the first condition we want to satisfy, its bias voltage is less than the E by C, VB is less than the E by C. Next condition is to satisfy the thermal energy. The thermal energy play an important role in the conduction of the single electron transistor, because at room temperature the thermal energy approximately will be 0.024, I think 0.02 electron volt. The thermal energy should be low enough, the the charging energy, because the charging energy E square by 2c, it will be large, then only the electron can flow through the quantum dot. If the thermal energy will be greater than this energy, then the thermal energy itself it's carry the electron to the drain region, from the source region to drain region. So you got to pull down the thermal energy. Then the charging energy should be greater than the thermal energy. If the charging energy is greater, then you can control the single electron transistor as your wish. The third condition, it should satisfy that tunneling resistance should be greater than the quantum resistance. The quantum resistance here, it is h by e square. The quantum resistance here, it's actually you can call it a Hall resistance in some quantum Hall resistance. It should be in discrete manner. So your tunneling resistance should be larger. Then only you can control the electron through the quantum dot. Here in this last list, we are going to see the sum of the application of the single electron transistor. The single electron transistor can be used as a charge sensor. That means it can detect the charge, how many charges are in the some material in some sources. So it can be used as a charge sensor. Then it can detect the infrared radiation. The single electron transistor can absorb the infrared photons, and it can tell the few photon infrared radiation can detect. Then it can detect the microwave detector, that means ultra sensitive microwave detector. So the microwave, you know that it is 10 centimeter wavelength or few kilometer wavelength. It's called a microwaves. So those can be detected using the single electron transistor. Then the next one, it can be used as a temperature sensor. The last point, single electron spectroscopy, we are using the nowadays the single electron transistor. Then super sensitive electrometer, we are using the single electron transistor. So that means here the cool in this lectures we studied the what is the Coulomb blockade effect. That means we are controlling the electron flow in discrete manner, that is called Coulomb blockade. Based on the Coulomb blockade, we studied about the single electron transistor, how one can control the electron flow through the barrier or through the quantum dot quantum wire in the discrete manner. That the single electron transistor, we just saw the schematic diagram as well as the energy level diagram. The next thing we studied about the how it should be looking like the current versus the bias voltage, because it is not like a continuous manner, it is a discrete manner. That means electron flow happened in discrete manner, because here Coulomb repulsion play an important role, because one electron can only allow through the transistor. So the current versus or charge versus voltage will be in the staircase structure. Then the final slide we studied about there are three conditions you need to satisfy if you want to construct the single electron transistor. That the thing we studied. The last slide explained the few application of the single electron transistor.